Deep in the cosmos, beyond the reach of human eyes, are objects so dense and so powerful that they stretch the very fabric of space and time. These objects are called neutron stars, and they are the remnants of stars that have died in the most violent, explosive way imaginable through a supernova explosion. The birth of a neutron star is a spectacular and dramatic event, one that marks the final chapter in the life of a massive star. But these incredible objects, small, dense, and mysterious, are remarkably hard to detect. They hide in the darkness of space, revealing themselves in subtle and unexpected ways. So, how do we find something so compact, so faint, yet so central to understanding the nature of the universe? The search for neutron stars is nothing short of a cosmic detective story, one that spans across light years, involves cutting-edge technology, and pushes the limits of our knowledge. To truly appreciate the challenge of detecting neutron stars, we must first understand how they come into being. Picture a massive star, perhaps 10 times the size of our Sun, living out its stellar life. For millions of years, this star burns brightly, fusing hydrogen into helium and producing light and energy. But as the star nears the end of its life, it runs out of fuel. Without the outward pressure of fusion to balance the inward force of gravity, the core collapses inward, causing an explosive supernova that leaves behind a collapsed, incredibly dense remnant, a neutron star. The core that survives is crushed to such an extent that neutrons, particles that normally exist within atomic nuclei, become the building blocks of the star. In this way, neutron stars are born, incredibly small, incredibly massive, and so dense that a single cubic centimeter of their material would weigh as much as an entire mountain here on Earth. Despite their extreme nature, these cosmic objects are surprisingly hard to find. Neutron stars do not glow like regular stars. Instead, they only reveal themselves indirectly through the extraordinary gravitational and electromagnetic forces they exert on their surroundings. The challenge of detecting them lies in the fact that they are so small compared to the massive stars that came before them, and they often emit very little visible light. One of the first clues to the existence of a neutron star comes not from light, but from the gravitational disturbances it creates. Neutron stars are often found in binary systems, where they orbit alongside another star. Although the neutron star itself might be invisible, its gravitational pull distorts the motion of its companion. In these systems, we see the companion star wobbling in its orbit, as though tugged by an invisible hand. This gravitational pull is strong, even though the neutron star's light is hidden from us. By carefully tracking the motion of the companion star, astronomers can deduce the presence of the neutron star and even calculate its mass, revealing just how massive these dense objects really are. The more we study these gravitational interactions, the more we uncover the presence of neutron stars that would otherwise remain concealed. But gravitational effects are just one way to detect these mysterious objects. Neutron stars are often surrounded by an accretion disk, a swirling mass of hot gas and stellar debris pulled in by the star's immense gravity. As this material falls inward, it is heated to extreme temperatures due to friction, glowing brightly in the X-ray spectrum. The radiation from this hot, dense gas is so intense that it can be detected by telescopes orbiting high above the Earth's atmosphere, where X-rays are absorbed by our atmosphere. Through these X-ray emissions, astronomers can observe the presence of a neutron star, even if it's hundreds or thousands of light years away. The study of these X-rays not only helps us locate neutron stars, but also gives us a window into the most energetic processes in the universe. These X-rays are a kind of cosmic fingerprint, revealing the internal workings of the neutron star. By studying the intensity and variability of these emissions, scientists can learn more about the star's mass, spin, and temperature, gaining valuable insights into the physical properties of these incredible objects. Perhaps the most iconic and mesmerizing way to detect a neutron star is through the discovery of a pulsar, a rapidly spinning neutron star that emits regular pulses of electromagnetic radiation. These pulses are like beams of light or radio waves, sweeping across space. When one of these beams points toward Earth, we detect a regular, rhythmic signal. Pulsars are essentially cosmic lighthouses, their beams of radiation rotating in perfect sync, creating a heartbeat-like pulse. This regularity is so precise that pulsars have been used as some of the most accurate cosmic clocks we know. In fact, the pulses from some neutron stars are so consistent that they are on par with the most finely tuned atomic clocks on Earth. These pulses not only reveal the presence of a neutron star, but also give us insights into the star's rotation and magnetic field. As the neutron star spins, its strong magnetic field accelerates particles to near-light speeds, generating the powerful beams we observe. By studying these pulses, we've been able to test Einstein's theories of relativity and even detect ripples in space-time itself, gravitational waves, produced by neutron star mergers. And then, there are gravitational waves, a truly revolutionary way to detect neutron stars. These ripples in the fabric of space-time are caused by the most violent events in the universe, including the collision and merger of neutron stars. When two neutron stars spiral toward each other and collide, they send out gravitational waves, distortions in space-time that travel across the cosmos at the speed of light. In 2017, the world celebrated a historic breakthrough, the first ever detection of gravitational waves from the merger of two neutron stars. This discovery opened up a new chapter in our understanding of the universe, allowing us to observe cosmic events that were previously invisible to traditional telescopes. The merging of these neutron stars also created a burst of electromagnetic radiation, including gamma rays and visible light, which were detected across the entire electromagnetic spectrum. Gravitational waves offer us a unique way to detect neutron stars, one that is not limited by light or radiation. These ripples allow us to observe the most extreme events in the universe, uncovering the very heart of the most catastrophic and awe-inspiring processes in the cosmos. As we continue to develop new technologies and refine our techniques, the future of neutron star detection is brighter than ever. New telescopes, more sensitive detectors, and the continued growth of gravitational wave observatories will allow us to explore even more distant and mysterious neutron stars. The more we learn, the closer we come to unlocking the secrets of these enigmatic objects and to understanding the most extreme conditions in the universe. Neutron stars are a testament to the sheer wonder of the cosmos, objects born from the death of stars, yet teeming with power, mystery, and insight. As we continue to study them, we uncover not only the nature of these extreme environments, but also the fundamental laws of the universe itself. Each new discovery is a step toward a greater understanding of the forces that shape our universe. Through the efforts of astronomers and physicists around the world, we're embarking on a journey to unravel the mysteries of neutron stars. And in doing so, we might just find answers to some of the most profound questions about the cosmos, space, time, and the very nature of reality.